Hey everyone, and welcome to a deep dive into TensorFlow 2.0. We're going to be taking a look at some excerpts from a Chinese textbook on the subject. And I got to say, I'm pretty excited about this one. So the main goal is to kind of help you guys get a handle on what's new and improved in the world of TensorFlow. And, hopefully have some fun along the way. We'll be talking about some pretty interesting stuff like, just-in-time compilers. And there's this really interesting connection to the way our brains learn.
Yeah, I think it's really cool how this textbook really focuses on TensorFlow 2.0's kind of practicality and how it really impacts developers in these real-world situations. It's not just about the theory, it's about how these changes make a difference and how we actually use TensorFlow day to day.
Yeah, I remember when I first started using TensorFlow 1.x, setting it up was a bit of a nightmare. And those static graphs, they weren't exactly a walk in the park to work with either. Sounds like TensorFlow 2.0 really takes these issues seriously.
Oh, absolutely. One of the biggest changes is the move to what they call Eager Execution, which makes TensorFlow way more interactive. You actually get to see the results of your code as you're writing it, which makes debugging a whole lot easier.
Okay, so for those of us who aren't exactly coding wizards, what does eager execution actually mean?
Okay, so imagine you're writing a program using Python, right? That's the language that TensorFlow uses. With eager execution, each line of code you write, it's executed immediately. You see the output right away. So it makes it easier to spot and fix errors.
So it's kind of like testing your code as you write it.
Yeah.
Instead of waiting for the whole thing to run and then trying to figure out where you messed up. That sounds way more efficient.
Exactly. And this actually ties into another major improvement. TensorFlow 2.0 fully embraces Keras as its go-to high-level API.
I remember hearing about Keras before. It's all about building deep learning models easier.
Yeah. Precisely. Think of it like building with Legos. Keras gives you these pre-built blocks for creating different layers of your neural network. So you don't have to write the code from scratch for each layer. You just pick and choose the blocks you need, connect them together, and boom, you start training your model. Imagine you want to build a model to identify different breeds of dogs. With Keras, you could have pre-built blocks for recognizing things like fur color, ear shape, tail length, and then you can easily assemble those into a working model.
That's a great way to put it. It sounds like Keras could make deep learning much more accessible to people who aren't hardcore programmers.
Yeah.
But I'm curious, doesn't simplifying things like this sometimes come at the cost of performance?
That is a great question. And the developers of TensorFlow 2.0 definitely anticipated that concern. That's why they introduced these two really clever tools, Autograph and TF.function.
Okay, I'm intrigued. What exactly are Autograph and TF.function?
All right, so let's start with Autograph. Think of it like a translator, okay? It converts your Python code into something TensorFlow can understand and optimize. So even if you're using standard Python features like if statements and for loops, Autograph is working behind the scenes to make sure your code can be executed efficiently by TensorFlow.
So it's like having a bilingual friend who can seamlessly translate your conversation with TensorFlow, make sure nothing gets lost in translation.
Exactly. And that's where TF.function comes in. It's like adding a turbocharger to your Python functions. When you decorate a function with TF.function, TensorFlow takes it and converts it into a graph, which can be executed much faster.
So you're still writing your code in Python, but TensorFlow is optimizing it under the hood to make it run as smoothly as possible. That's pretty impressive.
It is, and it really speaks to the overall goal of TensorFlow 2.0, to make deep learning more user-friendly. Without sacrificing the power and performance that experts demand, it's a delicate balance, but I think they've done a remarkable job achieving it.
Okay, so we've talked about how TensorFlow 2.0 is designed to be easier to use. But how does that actually translate into building and training neural networks? Let's dive into that a bit further.
Absolutely. So one of the fundamental concepts behind how neural networks learn is called backpropagation, which relies on something called gradient descent. The textbook actually uses a really interesting analogy to explain this. It compares gradient descent to a monk descending a mountain.
A monk descending a mountain.
Okay.
All ears.
Imagine a monk trying to find the lowest point in a valley. He might start at a random spot on the mountain and take small steps in the direction of the steepest descent. That's essentially what gradient descent does. It tries to find the minimum of a function, which in this case represents the error of our neural network, by iteratively adjusting the weights, or the strength of the connections between the neurons.
So the monk's journey down the mountain represents the algorithm's search for the optimal set of weights that minimize the error of the neural network. That's a pretty cool way to visualize it.
And what's even more fascinating is that even tiny changes in the way the network is set up can drastically change how quickly it learns. It's like the difference between the monk finding a smooth path down the mountain versus having to climb over boulders.
So it's not just about finding the right direction. It's also about finding the most efficient path to get there. Now, I know that neural networks are inspired by the way our own brains work. Are there other parallels between the biological brain and these artificial neural networks?
Definitely. One key component of both biological and artificial neurons is the activation function. Think of it like a dimmer switch. That controls how strongly a signal is passed on to the next neuron. It's the smooth control that allows for fine-grained learning and complex decision-making within the network.
So in a way, these activation functions allow the network to learn and adapt in a more nuanced way, just like our brains do.
Precisely. And the way these artificial neurons are connected and organized is also inspired by the structure of our brains, allowing them to process information in a hierarchical and efficient manner.
This is all incredibly fascinating. We've learned about how TensorFlow 2.0 has made deep learning more user-friendly, and we've even delved a little bit into the inner workings of neural networks themselves.
And this is just the beginning. There's so much more to explore in the world of TensorFlow 2.0, but for now, I think we've given you a solid foundation to build upon.
Absolutely. Stay tuned for part 2 of our deep dive, where we'll explore even more fascinating aspects of TensorFlow 2.0 and how it's being used to push the boundaries of what's possible with deep learning. Welcome back to our deep dive into TensorFlow 2.0. I'm still thinking about that monk descending the mountain. Such a great way to picture gradient descent.
It really is. It really highlights how these complex mathematical concepts can be understood through these simple analogies. And just like that monk finding the most efficient path down the mountain, in deep learning, we're always looking for the most effective ways to train our models.
Speaking of effective training, this textbook dives into a specific type of neural network that's become a real game changer. It's called a convolutional neural network, or CNN for short.
Ah, CNNs. They've revolutionized the field of computer vision. And they're used in everything from self-driving cars to medical image analysis.
But what makes CNN so special? What sets them apart from other types of neural networks?
Well, what's fascinating is how CNNs are actually modeled after the visual cortex in our own brains. You know, the part of the brain that processes visual information? Just as our brains have specialized cells. For detecting edges, shapes, and patterns, CNNs use something called convolutional layers to do the same.
So they're kind of like digital versions of our own visual processing system.
That's a great way to think about it. These convolutional layers act as filters, scanning the input image and extracting features at different levels of detail. It's like having a magnifying glass that can zoom in and out, focusing on different aspects of the image to understand what's going on.
I'm starting to see why they're so powerful for image recognition, but how do these convolutional layers actually work?
Okay, so imagine you're trying to identify a dog in a picture, right? The first convolutional layer might detect simple edges and lines, while the next layer might combine those edges to identify shapes like ears or paws. As you go deeper into the network, the layers learn to recognize more complex features, eventually being able to distinguish between different breeds of dogs.
It's like a hierarchy of understanding, building from simple elements to more complex concepts.
Exactly. And after these convolutional layers do their work, the extracted features are then passed on to something called pooling layers. These layers downsample the information, reducing the computational load, while preserving the most important features. It's like summarizing a long document. You extract the key points, discard unnecessary details to get the gist of it.
So it's all about efficiency, finding the most important information without getting bogged down in the noise.
Right. And finally, all of this processed information is fed into the fully connected layers of the network, where the final classification or prediction is made.
So we have convolutional layers, extracting features, pooling layers, summarizing the information, and fully connected layers, making the final decision. It's amazing how all these pieces work together.
It is. And the textbook even uses a classic example to illustrate this whole process. You've heard of the MNIST dataset, right? It's that collection of handwritten digits that's often used as a benchmark in computer vision.
Oh, yes. I remember seeing those images. It's like the hello world of image recognition.
Exactly. And the textbook walks you through the steps of building a simple CNN, using TensorFlow 2.0 to classify those handwritten digits. It's a great way to see how all of these concepts we've been talking about actually come together in practice.
So you're not just learning the theory, you're actually seeing how to build these models yourself. That's a really cool approach.
It is. And speaking of cool approaches, the textbook also talks about ResNet, or residual networks, which were a real breakthrough in deep learning.
ResNet. That name rings a bell. Wasn't that the architecture that won the ImageNet competition a few years back?
Hmm.
And achieved some incredible accuracy.
That's right. ResNet introduced this brilliant concept called STIP connections, which basically allow information to bypass certain layers in the network. This solved a major problem known as the vanishing gradient problem, which often hampered the training of very deep networks.
The vanishing gradient problem. What's that all about?
Well, imagine you're whispering a message down a long line of people. As the message gets passed along, it might get distorted or fade away entirely. That's kind of what happens with gradients, those signals that guide the learning process in very deep networks. As they travel back through many layers, they can become too weak to be effective.
So it's like the signal loses its strength as it travels through the network.
Exactly. And ResNet's skip connections act like shortcuts in that line of people, allowing the message or gradient to reach its destination without getting lost along the way.
So ResNet essentially found a way to build deeper, more powerful networks by making sure the learning signals could travel effectively. That's pretty clever.
It was a game changer. And it led to a shift from simply stacking more layers to thinking more strategically about how information flows through the network.
Okay, so we've gone from understanding the basics of CNNs to exploring a groundbreaking architecture like ResNet. But the world of deep learning never stands still, does it? Are there any other innovations in CNNs that the textbook touches upon?
There is one more I think you'll find quite interesting. It's the concept of attention mechanisms.
Attention mechanisms. I've heard that term before,
Yeah.
but I'm not sure I fully understand what it means.
Think about how you focus your attention when you look at a picture. You don't pay equal attention to every single pixel, right? You're drawn to certain areas or features that are more important or relevant to you.
That's true. I might focus on the person's face in a portrait or the details of a flower in a landscape photo.
Exactly. Attention mechanisms allow neural networks to do the same thing. They allow the network to focus on specific parts of the input data that are most relevant to the task at hand.
So instead of treating all the information equally, the network can prioritize what's important. That sounds incredibly powerful.
It is. And it's led to some amazing breakthroughs in areas like natural language processing and machine translation.
So it's not just about images anymore. These attention mechanisms can be applied to other types of data as well.
Absolutely. And the textbook gives some great examples of how attention mechanisms are being used in different domains. One example that comes to mind is how they're being used to improve the accuracy of machine translation systems by allowing the model to focus on the most relevant words in a sentence. Attention mechanisms can help produce more accurate and fluent translations.
That's incredible. So in a way, these attention mechanisms are bringing neural networks closer to the way humans process information, allowing them to be more selective and efficient in their analysis.
You got it. It's all about finding ways to make these models smarter and more adaptable, and attention mechanisms are playing a huge role in that.
So we've covered CNNs, ResNet, and now attention mechanisms. It's amazing to see how these ideas are pushing the boundaries of what's possible with deep learning. But I'm curious, does the textbook focus only on image-related tasks, or does it explore other applications of CNNs?
That's a great question. While CNNs are widely known for their success in computer vision, their ability to extract local patterns and hierarchies makes them surprisingly effective for processing sequential data like text as well.
Wait, a CNN for text? I thought those were mainly for images. How does that even work?
It might seem counterintuitive, but think about it. Text is just a sequence of characters or words, right? And just like a CNN can learn to recognize patterns in pixels, it can also learn to recognize patterns in these sequences.
So instead of analyzing pixels in an image, the CNN analyzes words or characters in a sentence. That's pretty mind-blowing.
It is. And the textbook actually demonstrates how a CNN can be used to classify text into different categories, like sentiment analysis, spam detection, or topic categorization. It's a great example of how these deep learning techniques can be applied to a wide range of problems, not just image recognition.
It's like showing that a master chef can create culinary masterpieces with a variety of ingredients, not just the ones they're most famous for.
I love that analogy. And what's even more exciting is that the textbook emphasizes how this text classification example can be extended to other sequential problems like time series analysis, speech recognition, or even music generation, showcasing the broader applicability of deep learning techniques.
It's like opening a door to a vast landscape of possibilities, with TensorFlow 2.0 serving as our trusty guide.
Exactly. And what's even more exciting is that this landscape is constantly expanding, with new research and applications emerging all the time. It's a truly dynamic and ever-evolving field.
It sounds like we've only just scratched the surface. of what's possible with CNNs in TensorFlow 2.0. This textbook sounds like an incredible resource for anyone who wants to dive deeper into this world.
It really is. It strikes a perfect balance between providing clear explanations of the technical concepts and showcasing practical examples of how to use these tools in real-world applications. It's both insightful and inspiring.
This has been an incredible journey so far. We've gone from understanding the fundamentals of CNNs to exploring cutting-edge techniques like ResNet and attention mechanisms. I can't wait to see what else TensorFlow 2.0 has in store for us.
Me neither, and I'm sure our listeners are eager to learn more as well. Stay tuned for the final part of our deep dive, where we'll wrap up our exploration of TensorFlow 2.0 and discuss some key takeaways from this insightful textbook.
Welcome back to our deep dive into TensorFlow 2.0. We've covered a lot of ground. From those fundamental changes in TensorFlow 2.0 to exploring all those intricacies of convolutional neural networks.
It really has been quite a journey. And I think what's really impressive is how TensorFlow 2.0 manages to balance this incredible power and flexibility with a focus on making deep learning more accessible, to a wider audience.
Absolutely. And this Chinese textbook we've been exploring really highlights that, it doesn't just dive into all the technical details, but it also showcases those practical tools and resources that TensorFlow provides to make that development process smoother and more intuitive.
Yeah. One thing that really stood out to me was the discussion of TensorFlow datasets and TensorBoard. These are invaluable tools that can really streamline your workflow and help you gain deeper insights into your models.
I've heard about TensorFlow datasets before. It's like a massive library of pre-processed datasets, right? So instead of spending hours cleaning and formatting data, you can just grab what you need and get straight to building your models.
Exactly. It's like having a well-stocked pantry. For your deep learning experiments, you can find datasets for everything, from image classification to natural language processing to time series analysis. It's an incredible resource. It saves you time and effort, allowing you to focus on the more creative and exciting aspects of deep learning.
And what about TensorBoard? I'm not as familiar with that one.
Oh, TensorBoard is a window into the soul of your neural network. It allows you to visualize the training process, track various metrics, and even peek into the internal workings of your model. Imagine being able to see how your model's accuracy improves over time, or how different layers are contributing to the final predictions.
That sounds incredibly useful. It's like having a dashboard for your neural network, giving you real-time insights into its performance and helping you identify areas for improvement.
Precisely. And the textbook does a great job of explaining how to use TensorBoard effectively, highlighting its key features and visualizations. It's a tool that can be beneficial for both beginners and experienced deep learning practitioners.
Speaking of beginners, I think one of the things that makes this textbook so valuable is its emphasis on practical examples. It doesn't just throw a bunch of theory at you. It walks you through the process of building different types of neural networks, step by step, using TensorFlow 2.0's intuitive syntax and APIs.
Absolutely. And it's not just about the code itself. The textbook explains the reasoning behind each design choice, the role of different layers, and how to fine-tune hyperparameters to improve performance. It's a fantastic blend of theory and practice that helps you develop a deep understanding of how these models work and how to build them effectively.
It's like having a seasoned mentor, guiding you through the world of deep learning, sharing their experience and insights to help you avoid common pitfalls and achieve better results.
I couldn't have said it better myself. The textbook even includes these historical anecdotes about the evolution of neural networks, which I found fascinating. It's amazing to see how these ideas have developed over time, from simple perceptrons to the sophisticated architectures we have today.
It really shows the power of human ingenuity and the relentless pursuit of understanding how our own brains work. And with tools like TensorFlow 2.0, we now have these incredible resources to explore and unlock the potential of deep learning.
So to wrap up our deep dive, what are some key takeaways you think our listeners should remember about TensorFlow 2.0?
Well, I think the biggest takeaway is that TensorFlow 2.0 has truly democratized deep learning. It's made these powerful tools and techniques accessible to a much wider audience, regardless of their background or technical expertise.
I completely agree. And this textbook is a testament to that. It provides a clear, engaging, and practical introduction to TensorFlow 2.0. Guiding you from the fundamentals to advanced concepts, with a perfect balance of depth and accessibility.
So for our listeners, I encourage you to dive in, explore the resources we've talked about, experiment with the code, and don't be afraid to ask questions. The world of deep learning is vast and constantly evolving, and with TensorFlow 2.0, you have the power to shape its future.
That's a perfect note to end on. Thanks for joining us on this deep dive into TensorFlow 2.0. We hope you've enjoyed the journey and are inspired to explore the incredible world of deep learning.